Hello, Chem 111 class. We're going to talk about calorimetry today, which is the other half of our second chapter. So the first half of the chapter talks a lot about different types of energy, and the second half is about how we can measure those energies. So here we have a definition for what a calorie is. A calorie is a scientific unit that's defined as the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. So a gram of water is actually a very small amount of water. It's around, a cube about that big. So a gram is a very small amount, and 1 degree Celsius is also pretty small. But if we had 260 kilocalories, so kcals there, 260 kcals, we know there's a relationship between calories and kcals because kilo is a familiar phrase for us. So here we have 260 kcals, and so we know that, for example, there's 1 kilogram per 1,000 grams. So in the same way, the same relationship applies here. There's 1 kilocalorie for every 1,000 calories. Okay, and so 260 times 1,000 gives us 260,000 calories. Okay, so that means that if I had 1 gram of water, I could raise the temperature from, say, 0 Celsius to 260,000 degrees Celsius. So that's very, very hot. So it's a good thing that we are made of much more than 1 gram of water. Otherwise, a very small amount of food would cause our temperatures to go up really, really high. Okay, sometimes we want to measure heat in joules. So the symbol for joules is just a capital J. And there is a relationship between calories and joules. There's, as it turns out, 4.184 calories, or joules, is equal to 1 calorie. So this could be used as a fraction again to do conversions. So the relationship could be written like this. Okay, or I could flip that fraction over, just like we've seen from how we learned the metric system in Chapter 1. Okay, so when we look at a package of food, it'll have like nutritional calories listed on there. And so, for example, I just borrowed this little package of goldfish crackers from my coworker's desk. And it says right on there that there are 200 calories. So whenever a nutritional label says 200 calories on it, the truth is that that's actually kilocalories. When they're saying 200 calories, they actually mean scientifically that that's 200 kcals. So then the question is, how many actual calories is that? Okay, so we're going to use that relationship between kilo and calories to convert. So we know there's 1,000 of the base unit for 1 of the kilos. And so when we eat a little snack, this bag is not a big bag, it's like meant to be a snack. When we eat a little snack of goldfish that says 200 calories, that's actually 200,000 scientific calories, okay? So for example, a Snickers bar, like a regular sized Snickers bar, has 260 nutritional calories. And so this question is going to be one that you can answer in Top Hat to get some credit for the lecture. Okay, so make sure you take a sec, pause the video, and go ahead and scroll down and read the question and answer that. Okay, so next we have a new concept called specific heat capacity. Okay, well, it's not really actually a new concept because actually you have an understanding of this concept already. So if I'm making a pot of soup and I put in a metal spoon into my pot and a wooden spoon, And then I walk away for a while and my soup is boiling and it's really, really hot, and then I come back to stir it. We know instinctively that grabbing the metal spoon would be a mistake, right? Because you would get burned. But I could probably grab the wooden spoon with relatively little injury. And the reason for that is that metal is really good at conducting heat, whereas a spoon is more of an insulator, so it doesn't actually conduct heat very well. So that means that the spoon has a very high specific heat capacity, which we are actually going to abbreviate the specific heat capacity as either S, SH in some texts, or as the letter C. You'll see it both ways depending on where you look on the internet and what part of your textbook you're in. So specific heat is the symbol C. Basically, the definition for specific heat capacity as a formal measurement is that it is the heat required to increase the temperature of 1 gram of something by 1 degree Celsius. So instead of just looking at water like we did on the last slide when we were talking about heat in general, in terms of calories, here we're talking about anything. It's not just water, okay? So a calorie is defined based on how much energy is required to heat up a gram of water, but specific heat capacity is applied to any substance, not only water. So in this case, if I had 1 gram of a wooden spoon, it would take quite a bit of energy to heat it up by 1 degree Celsius, which is why the spoon is the best choice to stir my soup with, the wooden spoon, not the metal spoon. Okay, so here is a nice factor that we should keep in mind. There is always 4.184 joules per gram times degrees C for water. So we can say the heat capacity here of water is always 4.184 joules per gram degree C. So this is a constant that we use really often. You'll be given that, right? It's part of your toolkit. You can pull that out whenever you need it. The units on this are funny because, again, we define it by the amount of energy, so that's joules. Let me change the color here. We define it by the amount of energy for every gram to raise the temperature every 1 degree. So that's why the units have such odd collection. Okay, so for example, if I had just 1 gram of water, I know that it would take exactly 4.184 joules to make the temperature increase from 0 to 1 degree Celsius. What if I wanted to go from 0 to 2 degrees Celsius, right? So in order, that's twice as much of a temperature change, so we would go 2 times the amount it requires to change the temperature by 1 degree. So total, this would get me a total here of 8.368 joules. Okay, so what if I wanted to raise 2 grams of my sample by 1 degree Celsius? The answer here is we got 2 grams, and if 1 gram requires 4.184 joules, then this is just dimensional analysis. So here we've got grams on top, grams on the bottom, and it's going to cancel. So that means that I've done my math right because I get an energy out of that. And so 2 grams would require 8.368 joules to raise the temperature by only 1 degree. Okay, so then similarly, if we wanted to raise 2 grams by 2 degrees Celsius, we're going to just multiply all of it together, right? So, and this way makes some sense because we had those funky units on our heat capacity here, but grams cancels here, and of course our degrees Celsius cancels there because I have one on the top and one on the bottom. So that leaves me with just the energy joules. And so as it turns out, if I wanted to heat 2 grams of water up by 2 degrees Celsius, it would require 16.74 joules of energy. Okay, so what we've just done here is we take mass times the change in temperature times the heat capacity, and it tells us how much energy is required for that process. Okay, so the equation that we're going to use in general is mass, so M, times the heat capacity, which again, sometimes they use C, sometimes they use S, but it means the same value, times the change in temperature, delta T. So this little triangle here is read as delta. It's a Greek letter that just means the change. So often we'll see delta T, sometimes we see the change in energy, which we saw in the other lecture. But basically it just means that you take the final measurement minus the initial measurement, and that's how you get delta T. Okay, so this S variable here, this S is constant for each type of material. So, for example, water always has a delta S, sorry, not a delta S, just an S of 4.184 joules per gram degree C. Other things have different heat capacities. So like even ice has a different heat capacity. It's around 2 joules per gram degree C, which is much lower. So ice doesn't absorb heat as well as liquid water does. Okay, so the state of matter will change this value, and the type of material in question will change this value. Sometimes we look this up and we use this known value of a particular material to calculate other variables in our equation here. Or sometimes we're trying to find S. We're trying to solve for S. Okay, so we're going to go through some problems here. We'll pick up in the next video with this slide.